Okay, let's continue with the block level design. This time we would like to use this technique to build a binary multiplier. Specifically, a 2-bit binary multiplier. It multiplies 2 bits A and B together. Now, in ordinary multiplication, we do the multiplication like this. A0 is multiplied by the B number, and we get this. And then A1 is multiplied by the B number. And then we add the result together. And this is the result. Here we have a C0, which is equal to the AND of these two together. Now, C1, the output here, C1, is the AND of these 2 bits together, added with the AND with these 2 bits together. C2 will be the carry out of this addition added to the AND between A1 and B1. And then you might have a final carry out. Now C0 is the AND between A0 and B0. So if we get an AND gate and we connect to it A0 here and B0, then we have the first output of our multiplier, which is C0. This output C1 is the AND between these two added with the AND between these two. So we get this AND together with this AND added using a half adder. I do not need more than a half adder here because this is only two bits added together. The one coming out of this gate and the one coming out of this gate. Now this is C1, which is the other output of our binary multiplier. The carry of the half adder is taken as an input to the next stage here. The carry out of this is going to be added here to the output of this AND gate, which has A1, B1 to the full adder. And the output of this full adder is C2 and the final carry, which is C3. And this is the circuit that we are looking for. It multiplies 2 bits B0 and B1 with A0 and A1, and we get the output at the C here, C0, C1, C2, and C3. Now let's go a little bit further. A 3-bit binary multiplier. Okay, we multiply 3 bits A0, 1, and 2 by B0, 1, 2, and 3. We do the same thing with the multiplication. This here is the multiplication of A0 with this number. These are the results. Now we multiply A1 with the B number to get this result here. Now we multiply A2 with the B number. Notice the shift to the left. Ordinary multiplication. Okay, this is the first output here, which is C0. This here is the second output, the third, C3, 4, 5, and 6. Okay, how do we get C0? It's an AND gate that has 2 inputs, A0 and B0. But now, notice this. I can make the addition here between these 3 bits and a 0, or 4 bits. I can use a parallel adder, a 4-bit parallel adder, the output of which is C1, which is the second bit in the output, and the output here, and here, and here, and the carry out of this parallel adder are added using another 4-bit parallel adder with these bits, this one, and this, and this. And the result of this second parallel adder will be C2, C3, C4, C5. And the carry out of this one will be the last bit in our answer. So this is the multiplication again. And This is the first 4-bit parallel adder that adds this one, and this one, and this one, and a 0. And these are here. And the 0. It is added with this here, which is this one here, which is this one, and this one here, which is this, and the last one here, A1, B3, is here. Now, the output C1 is alone here. The output from this parallel adder is taken here to the input of the second parallel adder, like so. Okay? And then the output here is taken as an input to the second one, and the third output, and the K here, which comes out of this, is the last bit to be added for this number here. Okay? And then A2, B0 is this bit here. A2, B1 is this bit here. A2, B2 is this bit here. And A2, B3 is this one. And the output carry from this parallel adder is C6. The output carry here is C6. Now, this is the complete circuit. C0, as I told you before, it's A0, B0. It comes out of this AND gate immediately out. And this is the first parallel adder. And this is the second parallel adder. And these are C1, C2, C3, C4, C5, and C6. C6 here is the carry out of this parallel adder. It should be noted that this output here is the carry of the first parallel adder and goes into here. Okay, let's use the same technique to design a magnitude comparator. What is a magnitude comparator? It compares two binary numbers together to find out whether A is bigger than A and B, or A is less than B, or A is equal to B. We will build here a 4-bit magnitude comparator. It has two inputs, A, which is a 4-bit, and B, which is a 4-bit, and we want to find out and we want to design a circuit that compares these two. Okay, now, when is A greater than B? Looking here, when is A greater than B? It is greater than B if this condition applies. If A here is 1 and B here is 0, that means A is greater than B because this is the most significant bit in A. If A3 is bigger than B3, that means A is bigger than B. And that occurs only if A3 equals to 1 and B3 equals to 0. And that can be verified from the expression A3 ANDed with B3 bar equal to 1. So whenever you have this condition, A is greater than B. Where else? If A3 is equal to B3 and A2 is greater than B2, meaning A2 equals to 1, B2 equals to 0, while A3 equals B3. Okay, let's say that the condition A3 equals B3, let's name it X3. So when X3 is equal to 1, and A2 equals to 1, and B2 equals to 0, that means A is greater than B. Okay. If A3 is equal to B3, and A2 equals to B2, and A1 is equal to 1, and B1 equal to 0, that means A is greater than B. And how is that satisfied? A3 equal to B3, that means X3 is equal to 1. And let's name the other condition, A2 equals B2 x2. And A is equal to 1 and B equal to 0. If the AND of these three values together is 1, that means A is greater than B. All right, the last condition is that these 3 bits, corresponding bits, are equal and A is equal to 1 and B equal to 0. That means if x3 ended with x2, ended with x1, ended with a0, ended with b0 bar is equal to 1. Here we named x1 is being a1 equal to b1. Okay, these are the conditions. Now, when is this equal to 1? If we take A3 as an input to an AND gate and B3 bar as an input to the same AND gate, and we get a 1 here, that means A is greater than B. All right. If we take an AND gate here, we put X3 as an input and A2 and B2 bar here. This is B2 bar. If this is 1, then this condition is satisfied. The third relation here, we can apply an AND gate where we have X3, X2, A1, B1 bar as inputs. Okay, if this is equal to 1, then this is satisfied. The last one, we have X3, 2, 1 as inputs, A0 and B0 bar. Now, if any of these is equal to 1, that means we put an OR gate and we connect these two to this OR gate. If any one comes here, that means a 1 will be the output of the OR gate, which will indicate that A is greater than B. Now, X3 here is equal to 1 if A3 and B3 are similar. Okay, so we put an exclusive NOR gate here. This is the exclusive NOR gate. If this is 1 and this is 1, the output here is 1. If this is 0 and this is 0, the output here is 1. So whenever X3 is 1, that means A3 is equal to B3. That means this condition is satisfied if these two other conditions exist. Now to have this input here, which is X3, we take a line from the output of this exclusive NOR and we connect it here. And to get X2, we put an exclusive NOR gate here, which has the input A2 and B2, and the output of which comes into X2. X1 is an exclusive NOR gate also, that has the inputs A1 and B1. And the final result that will come out is this. No, this is the exclusive NOR gate here. The exclusive NOR gate here. Okay? And we can follow the same technique. Now what we found so far is this part here. A greater than B. We can do this, we use the same technique to find out the circuit for A less than B, and we do the same thing to find out the circuit for A equals to B. Now notice, A equals to B, that means A0 is equal to B0, and A1 is equal to B1, and A2 is equal to B2, and A3 is equal to B3. And this, of course, that means getting the output of these NOR gates together into an AND gate. This is equal to 1 only if this is equal to 1, and this is equal to 1, and this is equal to 1, and last is X3 equal to 1. Okay, this is a simple exercise here. It says a 4-bit unsigned binary number, A, which is this, is fed into a 4-bit parallel adder as shown below. Notice here, A line is taken from A1 into Y0, from A2 into Y1, from A3 into Y2. Y3 has a 0, and the carry n to this one is equal to 0. Now, if A is equal to 6, this is the Y number here, or the B number here, will be what? This here. This one comes in here, and this one comes in here, and this one comes in here, and this 0 is the blue one here. It's like shifting to the right. This is equal to 6. Shifting to the right will result in a 3 value here. Okay? So the output here will be the addition of 0 plus 1 plus 0, which is 0, which is 1, I'm sorry. 1 plus 1 is equal to 0 with a carry of 1. 1 with a 1 and a 0 will give a 0 with a carry of 1. 1 plus 0 plus 0, we get a 1. And there is B4, which is C out, is equal to 0. So the output here is 9. 6 plus 3 is equal to 9.